Hi, today we're going to begin our chapter on probability. It is not possible to talk about statistics without having at least a little understanding about probability. So we'll remind you today of things that you've learned previously. We'll maybe introduce you to some things that you've not heard of before. Either way, we're going to get a little bit of grounding in the study of probability. So I'd like to start out with a little bit of vocabulary. I called it fundamental facts, and that's the truth. You'll hear these words often. An event, folks, is an individual outcome or a set of outcomes. For some random process. So we talk a lot about events happening in probability. An event might be flip a coin and get a head, or an event might be flip 3 coins and get 3 heads, right? An individual outcome or a set of outcomes for some random process. Probability, folks, in its bare bones, is the likelihood that some event will happen. Likelihood that some event occurs. Good. And as far as notation for probability, we're familiar with this because we've used it previously, but this symbolization, P of A, means the probability that event A happens. P on the same hand, P not A, that's the probability that A doesn't happen. And we can add a little bit to this, the probability that A doesn't happen. This is called the complement, or another name for it is the complement of event A. And numerically speaking, the probability of not A, it's the same thing as 1 minus the probability of A. Okay? If you remember, an event either has to happen or not, and the total likelihood for some event is 1. So if you don't get it, then the probability of that happening is 1 minus the probability that it would have happened. And now for a definition, or a working definition for probability. For equally likely outcomes, the probability that event A occurs is, well, you've seen this before, it's the number of times it did occur, or the number of times it happened, over the number of times you tried. Right? Those would be talking about an experimental probability. Theoretically, it would be the number of favorable outcomes divided by the total number of possible outcomes. And we often do talk about probabilities in 2 different ways. What happens when you actually try it, experimental probability, theoretical probability, what math says should happen. Very good. A probability distribution, folks, is the set of all possible outcomes to some random experiment. So it's the set of all possible outcomes along with their probabilities and the sum of probabilities. The sum of those probabilities has to be 1. And so, we want to talk a little bit, again, vocabulary. The sample space, folks, that's just the listing of all possible outcomes. And we're going to construct a little probability distribution here, the listing of all possible outcomes. Okay, it says that we should create a probability distribution for flipping 3 pennies and counting the number of heads. So we need to begin by listing all the possible outcomes for when you flip 3 coins, and then we'll worry about putting a probability along with those. So I'd like to have you just think about this for a minute. One possible outcome would be heads on all 3 pennies. Would you agree to that? That sounds pretty reasonable. Now, it could be possible that you only get heads on 2 of your pennies. So it could be like this: I had the first coin, I had the second coin, but not the last. But there are other ways that you could get 2 heads. So you could get a head and then sandwich a tail and then get another head. Or you could get a tail first and think that you were unlucky, but then come up with 2 heads, correct? So let's see, we've accounted for all 3 heads, 2 heads out of the 3 coins. Now we got to think about only having 1 head. And that could happen also, I think, you'll see quickly, in 3 ways. You could get that 1 head first, you could get it second, or it could come up on the last coin that you toss, right? You would be thinking, ooh, I don't think I'm getting that head, but then it finally comes up. Now I think that we've accounted for 3 heads, 2 heads, 1 head. The only other possibility is that no heads at all come up, and that would be very unlucky. So this is our sample space, folks. Okay? A listing of all the possible outcomes for the experiment, flip 3 coins or 3 pennies, our sample space. In order for us to talk about a probability distribution, though, we have to have, it says, all the possible outcomes, which we have covered, but we have to have a probability for each of those, and the sum of all those probabilities has to be 1. So I would love to have you think about this. I think that we're going to be able to synthesize a little. We had 1 outcome where all 3 coins were head. We had 3 outcomes where 2 of the coins were head. And we had, let's see, 3 outcomes where just 1 was head. So I think that we can do a little bit of synthesizing here. I'm going to put titles on my table here. The number of heads is what we were counting, and probability is good. But one of our outcomes was 3, because we had 1 case where all 3 coins came up heads, and the probability of that happening is 1 time out of, oh, we didn't count, 1, 2, 3, 4, 5, 6, 7, 8. So 1/8 of the time we could expect to get 3 heads. Then we had to look at things where we had only 2 heads come up, and 3 of our 8 possibilities had that type outcome. We next listed all of those that had 1 head come up. There were 3 outcomes like that, and finally we had 1 outcome where there were 0 heads. That also had 1/8 of a chance of happening. Now, to qualify as a probability distribution, we've got 2 of the bases covered. We have the list of all our outcomes, we have probabilities for each one. We got to just check and make sure that those probabilities add up to 1, and you can see real quickly they do. 3 plus 3 plus 2, yep, that's 8, and 8/8 is 1. So we've listed a probability distribution for the experiment, flipping 3 coins, the number of heads. We cannot talk about probability without referring to this law of large numbers. Okay? I think that we're all familiar with it, because if I asked you over time, if we flipped a coin 1,000 times, you could tell me about how many heads I should get, because the more often you do something, the more often what should happen will happen. Like, I could flip 10 times and get 10 heads. right? That's not outside the realm of possibility. But if I'm flipping 1,000 times, I know that the more often I do it, the more likely what should happen will happen, okay? The more times you try, the more often what will happen is what should happen. And that just makes sense. The law of large numbers. Okay. As you can see, for this part of the lesson, I found an online coin flipper program that will let us enter the number of tosses that we want to look at, and it will show us our results, the number of heads out of the total number of tosses, the number of tails out of the total number of tosses, and it will give us a ratio as we go through. Now, I'd like us to start small, so we're going to begin, I think, with 10 tosses. And if things were working according to mathematics, we should come out 50-50. Let's see how that works here. Oh, well, we got close now. We are 60-40 in 10 tosses. Now, the law of large numbers says that as we increase the number of attempts, the more often what should happen will happen, and so our percentages should get closer to 50-50. I'm going to up the ante a little bit and go for 50 tosses, 50 more. You'll see that we're accumulating things here. So let's toss 50 more times. This gives us a total of 60 flips, and we should come out, ooh, that's closer. We should have come out 30-30. I wonder what happens if we go for a broke and, like, say maybe do 500 now. This is going to put us to 560 total tosses. Oh yeah, that is very close, folks. We're real close to half and half. I wonder how far this will let us go. I'm going to go for 1,000. All right, look at that. Very close to 50-50. The law of large numbers stipulates that the closer or the more often you do something, the more often what should happen will happen. And so just by mathematically speaking, we should really hover around the 50-50 mark. Okay? I want to go back to your notes page here for just a second. See. Okay, we want to end our lesson on this thought. The fundamental principle of counting, which may not seem very major when you first hear this said and see it written down. However, it's the basis for which probability works. And it says, the fundamental principle of counting says, if one event can happen m ways, if one event can happen m ways, and a second event can happen n ways, then the total number of ways that both can happen together is m times n. Okay? If one event can happen m ways and a second event can happen n ways, then the total number of ways that both can happen together is m times n. It doesn't sound like a lot again. However, it does give us the basis for finding a lot of times the bottom number in a probability. So check this out. If you've read this section in the book, you'll know that it talked about Jack and Jill. So I have Jill in here. Suppose that Jill has 6 dresses, 3 little aprons, and 4 pails. How many different combinations of 1 dress, 1 apron, and 1 pail can Jill choose when she's getting ready to go up the hill to fetch her pail of water? Well, I'll tell you what, the fundamental counting principle says if she has 6 dresses, so the event dress, choose a dress, can happen 6 ways. The event choose an apron can happen 3 ways. And the event choose a pail can happen 4 ways. And ladies and gentlemen, the fundamental principle of counting tells us that if we multiply those things together, we'll get the total number of combinations that all 3 things can happen. So 6 times 3 is it's 18. 6 times 3 is 18, and 18 times 4, 72. There are 72 different combinations of dress, apron, and pail that Jill has available. Again, that would be perhaps the bottom of a fraction that says what's the probability she picks the red dress, the blue apron, and the silver pail, right? That would be 1 out of 72. Total of 72 different ways that she can choose one of each item. Here's a little probability question for us. Suppose it says you flip a fair coin 7 times. How many outcomes are possible? Well, folks, the fundamental principle of counting again says if you're flipping a coin 1 time, there are 2 possible outcomes. Would you agree to that? And for each of those 2, on the second flip, there are also 2 possible outcomes. And for all of those that we've taken care of next, the third flip will also have 2. In fact, you can see where this is headed. The total number of possible outcomes for this would be 2 to the 7th power, which I do not know off the top of my head, and I probably should. 2 raised to the 7th power. 128. What's so? 128 possible outcomes or possible sequences of heads and tails. All right, that's interesting. We said that that could be the bottom number in a probability, and in fact, it can. The probability that you get all 7 heads, that would just be 1 of those 128 possible outcomes. So here's the notation. Probability of 7 heads is equal to 1 in 128. The next question may seem like it's very difficult to answer, but I think that we can logic our way through it. It says, what's the possibility that you'll get 6 heads? That may seem like it's a little bit difficult to figure out, but if you put your mind to it, you'll find that it's not really. I mean, really, if you're going to get 6 heads, that means that one of your coins had to be a tail. Are you with me right there? And I think that there are only 1, 2, 3, 4, 5, 6, 7 ways that you can have one thing come up tails. So I believe that the probability that you get exactly 6 heads is 7 out of 128. Okay? That's not so hard to think about. I mean, once you wrap your head around the idea of probability, you'll find that you can logic a lot of it out. Okay? All right, that's it for today. I hope that you'll get out there and try that. You try at your earliest convenience, and we'll see you in school.